Hello and welcome. In this video, we're going to be taking a look at some basic techniques for solving common kinds of equations, specifically linear equations and quadratic equations. Now, when we're trying to solve an equation, what we're really trying to do, we're trying to find the certain values for a variable that satisfy that equation. And those values are called either solutions or roots. Well, let's start off with linear equations because it really introduces us to a couple of the basic properties of equation solving. First of all, just remember that we are looking for solutions to an equation, or another word for a solution is a root of that equation. And we're going to be using two main properties here. Our first property that we're going to be using all the time is the addition property. That's where whenever we've got an equation with one side, let's call it A, equal to another side of the equation, we'll call that side B, we can always add C some value to both sides without changing any of the solutions. Two equations are only equivalent if they have the same exact solutions. And if you think about an equation like it's sort of a balanced scale, of course, when an equation has an equal sign, things are balanced. We can always add the same amount to both sides of a scale or a teeter-totter, and nothing changes, it stays balanced. So we say that it has the exact same solution set and the two sides are still equal to each other. The other really common property is our multiplication property. Once again, if we start off with just a general equation, where we've got two expressions, one expression is A and one expression is B, with an equal sign in the middle, then we can always multiply both sides of that equation by some non-zero value. It's important here when I'm multiplying by C, C is not equal to 0. Okay, these two basic properties are going to kind of form the basis for all of the strategies for solving linear equations. And we'll start with that. First of all, what exactly is a linear expression or a linear equation? We say a linear expression is just a polynomial, so it has a coefficient in front of our variable. But our variable, in this case x, can only have a power of 1. We can always have a constant term in there as well. So we really have a linear expression in the form of ax plus b, where a and b are constants, and x is our variable. A linear equation, on the other hand, of course, needs a little bit more. Equation has an equal sign. A linear equation is any equation equivalent to ax plus b equals 0. It's important to note that a linear equation in x can take on many different forms, but it should always be equivalent to something of the form ax plus b. We usually need to make it equivalent ourselves by using the two properties, addition and multiplication. Okay, well, let's see how we can use the addition property and multiplication property for equations that are equivalent to this ax plus b equals 0 to be able to isolate x and get our roots or solutions. Okay, starting us off, we're looking to solve an equation, so we want to figure out what those roots are or what are the solutions. We need to find out what x is so that both sides of the equation here are equal to each other. Now, it might look a little bit linear because right now you don't see any powers on x and nothing else beyond simple addition, subtraction, and some coefficients. We're going to start off by distributing this negative sign using the distributive property. That gives us a minus 2, and when we distribute a negative onto minus 5x, we're going to add 5x instead. And really, we're just simplifying so far. We haven't used any equation properties. 3 minus 2 can be simplified to 1 plus 5x, and that's equal to 7x. It's at this point in time that we've simplified the left-hand side to be a linear expression. We've simplified the right-hand side to be a linear expression. There's not much else to simplify. Now we need to use either property number 1, the addition property, or property number 2, the multiplication property. Seeing that we have x's on both sides of the equation here, I'm going to probably want to use the addition property. Now, we never really said that c had to be positive. We can always add a negative. That's really just subtracting. The addition property is also basically a subtraction property as well. In this case, I'm going to use that property to subtract 5x from both sides. And I'll label that as using property number 1 there. Now, taking away the 5x from the left-hand side leaves us with just the constant term 1, and 7x minus 5x just leaves us with 2x. Okay, at this point in time, still a linear equation, but now I've got all my x's on one side of the equation. At this point in time, it seems like I just need to get rid of this 2. Now, this is a multiplication property, so I need to figure out what I need to multiply by. And if I've doubled x, I can get rid of that by multiplying by 1/2. Now, this is really just equivalent to dividing by 2. So in many cases, we can think of this multiplication property as essentially being division as well. Division by anything other than 0. We can simply divide by 2 by multiplying by 1/2. So this is equivalent. I'll label that as property number 2 being put to use there. And we get our solution, 1/2 times 1, and 2x times 1/2. Those 2's and the 1/2's cancel, and we left with our x. And that's our solution. So it's pretty straightforward, a little bit of simplifying, and then using these 2 properties. All right, well, in this next example, this certainly doesn't look very linear as it stands. Sure, we've got a whole bunch of x's, and they seem to be not raised to any power, so it feels a little bit linear, but we've also got a big rational expression, the whole thing on the left-hand side over 4. We have to do a little bit more rearranging to get things to look a little bit nicer. First of all, we'll just try playing around with the linear expressions in the numerator. We can distribute that 7 across, and it's negative, so we get negative 7x, and then we're going to also have our minus 7, all of that divided by 4. I can then collect some of those terms, and that's just simplifying further. We're left with 3x minus 7, all divided by 4. We have a linear expression over 4, and we can't simplify that linear expression any further, but we certainly could get rid of that 4. We can multiply both sides by 4 using the multiplication property, number 2, and that will cancel the 4 in the denominator, and we're just left with 3x minus 7. On the right-hand side, we have 8. Now, I'm going to use addition on both sides by adding 7 to both sides here, the addition property, property number 1, and that leaves us with 3x is equal to 15. We're one step away, and we're just going to multiply by 1/3. Now, maybe in this case, I'll just write that as division, but that's the same thing as multiplying by 1 over 3 using the multiplication property. And that leaves us with one single root, x is equal to 5. Now, I think it's important to be able to at least explain these steps, even if they're fairly basic. You don't always have to show this division by 3 or maybe adding 7 to both sides and things like that. But knowing how these properties are actually involved to get to your solution, that's the important part. Math is the technique that we use to explain how you got to your answer. And also try to organize your work kind of like this, I would say, where when you're doing something to an equation, try to keep those equal signs lined up. Sometimes that doesn't always work, especially when you move a whole lot of terms from one side to another side. Maybe you can't get all your equal signs lined up, but it's certainly a lot better to work down a page than to write an equation next to an equation and then working your way like you're, I don't know, writing an English essay. All right, well, let's do one more example that doesn't look linear right off the bat. Here, in this example, we've got 2 rational expressions, a single rational expression or fraction on each side. Now, in this case, our variable's actually always in the denominator, which is a little bit strange. That makes this not a linear expression. 4 over x is not linear at all. But somehow, through some transformations, we might be able to make this thing look linear. And what we're going to be using is a very common technique that is usually referred to as the cross multiplication technique. That's where when we have a single fraction equal to a single fraction, we're going to use properties of equivalent fractions first. We can always take a over b, and we can multiply that by anything on the top and bottom that basically makes a 1. d over d, for instance, is equivalent to 1. Multiplying by 1 keeps the value the same. On the other side, c over d, I'm going to multiply by 1, but I'm going to use a specific 1, in this case of b over b. Now, when we do that, we end up on the top here of a times d, if I reorganize, and b times d, if I reorganize. And on the right-hand side, we have b times c and b times d, just putting things into alphabetical order. Okay, well, we've got two equivalent fractions, and these two equivalent fractions have the exact same denominator. And for that to be true, they must have exactly the same numerators. A times D has to be equal to B times C. And we skip past all of those steps here by kind of just seeing that the A and the D are diagonally across from each other on the equal sign, and the B and the C are diagonally across each other from the equal sign. So AD equals BC is what we get when we do cross multiplication. Now this cross multiplication technique is very valuable in this particular case because when we cross multiply, we get rid of fractions. We can have the numerator from the left-hand fraction multiplied by the denominator of the right-hand fraction. And it doesn't really matter too much of an order here. We have to have the denominator x times a 2, or 2 times x if you prefer. And right away, this looks a lot more linear. We can expand out the left-hand side. That's just simplifying. There's nothing to really simplify on the right-hand side. And then we need to use some properties of equations. We want to put some of these terms together. We're going to need to make sure that we subtract 2x from both sides to gather our x's. So that's going to be using property number 1. But while we're at it, we can also be adding 4 to both sides. We're really adding a linear expression to both sides of the equation now. 2x taken away from 4x leaves us with 2x. And 4 added to negative 4 cancels. And we've canceled the x's on the other side and left us with 4. Well, 2x equals 4. We divide that by 2, and that's the same thing as multiplying by a half. That's the multiplication principle, leaving us with x equal to 2 as our single solution. Now, right away, these are just some classic examples of things that kind of don't look linear, but eventually you can turn them into a linear equation. You see this all the time in various different applications, but most of those will have lots of different symbols, and maybe, depending on your application, there's very few numbers involved. All right, here's an example of what I was just describing. This is some kind of an equation. Looks like it involves maybe masses, acceleration, maybe the gravitational acceleration at the Earth. Well, okay, there's very few numbers in here other than we have at least a 2 in there. But these properties always just hold, and we can use them in the same ways that we would if we were just trying to solve for x equal to a number. We might need to rearrange this equation to maybe have capital M by itself in terms of all of the other quantities. And right away, if you're trying to solve for something in the denominator, that's a bad place for it to be. We usually need to find a way to get an equivalent equation with m in the numerator, or maybe without any fractions at all. There's a couple different ways you can do this. You could multiply both sides by the denominator, just taking this m plus 2 little m, multiplying both sides. That would be one way to cancel it. Another thing I would always recommend too is you can make this a into a fraction, and then you're essentially just cross multiplying. Both of these get you to the same result. That allows us to take the a and multiply by capital M plus 2 little m. And on the other side of the equation, we're going to have this 1 times 2mg, which is just 2 little mg. It's the exact same thing you would have gotten by multiplying by capital M plus 2 little m and then canceling the denominator. But this is a quick way of doing it. Now, if m is inside the bracket, the thing we're trying to solve for, that's not a good place for it to be either. That usually indicates that you should go and try to expand things out using the distributive property. A times big M plus A times 2m. Now, when we're distributing there, we're going to see that we have a constant. That's a coefficient. Coefficients really should be out in front so that when we're adding like terms together, we're just going to be adding the numbers in front, the coefficients. On the other side, we have 2 little m little g. Perfect. That's kind of unlocked the variable or the symbol that we're trying to solve for. It's no longer in a denominator. It's no longer in the brackets. We've broken it free of its little jail, and now we're going to be using some properties of equations to get it by itself. We're going to move some of the other terms away. So first of all, we want to take this 2 times a times m. It doesn't have the variable we're looking for. We're going to isolate capital M by subtracting that from both sides. Okay, so in this case, you can see that we have subtracted, that's the same as the addition property, property number 1. I haven't really written down what I've added or subtracted to both sides, and that's okay. Last but not least, I'm going to divide by this coefficient. Last but not least, I have a times m. I really need to get rid of that a. So I need to divide by a. Dividing by a is just the same thing as multiplying by 1 over a. I'm going to have a in my denominator. And then on the top here, I have 2mg minus 2am. Typically, if you want to make this equation more useful, it's better to factor. We have a common 2 on the top. We have a common m on the top. And we just have g minus a all divided by a. I forgot to mention that, of course, when we multiplied by 1 over a, that was the multiplication property that we used. We used both there again. And if there's anything left to simplify, probably a good idea to do. But unfortunately, the only common factors across the top are 2 and m. We don't have a common a to cancel with this a. These two a's, unfortunately, can't cancel because a is not a common factor of everything on the numerator. Perfect. Well, with that, we've kind of wrapped up a lot of linear equations. We're just going to raise the degree by 1 more. Let's take a look next at quadratic equations. Okay, just like with linear equations, a quadratic equation is a whole family of equations that are all equivalent. However, unlike linear equations, we get a little bit more complex here. A quadratic equation is always going to be equivalent to something of the form ax squared plus bx plus c equals 0. We call this a quadratic equation, but also it's a polynomial. There's actually 3 terms in here, so technically this is called a trinomial because we have 3 terms. However, if b is equal to 0, then we would only have 2 terms, and we would call that a binomial with only 2 terms. However, we do need to kind of restrict so that a is not equal to 0, because if a was equal to 0, we'd be back down to just a linear equation. When we're solving quadratic equations, we're often using the zero product property. The zero product property says that whenever I've got 2 expressions, let's just use capital letters for full expressions, a times b, and if that product of 2 expressions is equal to 0, that must be true just by properties of our real numbers if and only if either our first expression a is equal to 0 or if our second expression b is equal to 0. And those can be very small equations and sometimes only linear. So we're really going to be using a lot of factoring here to try to break a quadratic equation down, preferably into a couple different factors in a product. And then we can use the zero product property to simplify into smaller equations, typically linear. This makes factoring wildly important, and it's pretty much important in no matter what kind of branch of computational mathematics you're doing. Factoring is wildly important in calculus, just because it comes in so handy to break large equations down into smaller ones, or large expressions into smaller ones. Let's start off with the basic factoring when a is equal to 1. This is kind of the easiest case to factor a trinomial. Now, the basic idea behind factoring here is that we're going to be looking for something of the form x squared with a coefficient of 1 plus bx plus c, and hopefully we can find an equivalent or equal expression here. Hopefully we can find these 2 linear factors. Now, we know that when we're putting an x in here, that x times x is going to get us our x squared. So that's going to be kind of the first term in each of these smaller linear factors. But then we really don't know what these 2 other numbers could be. I'll just call them p and q, for instance. That's our goal. Let's see if we can figure out what p and q are when we already know what our b and c are given to us as. Now I'm going to expand the left-hand side out, and this is going to be distributing twice, or using FOIL. X times x first gives us x squared. The outer 2 terms, x and q, multiply together, with q being our coefficient in front of the x. The inner terms, p times x and p times q. Okay, now that's still supposed to be equivalent to our unfactored polynomial here on the right-hand side, our quadratic. I'm going to also just do a little bit of grouping here. The first term, x squared, grouping the middle two terms, we can go ahead and use our factor, p plus q times x, using our distributive property. And then we have a pq. All right, this is still supposed to be equivalent to whatever quadratic that we're given. At this point in time, both sides of the equations have some things in common. Well, I guess the first thing they have in common is that the x squareds on both sides have exactly a coefficient of 1, so that's great. Then all of the x's have a coefficient, and we have all of the constants on either side. What we can do, because these are going to be equivalent, in order for that to be true, they need to have the exact same number of x's on either side, and the constants on either side also need to be equal to each other. If we equate these coefficients from the left and right hand side, we get kind of an idea of how we factor. First of all, the p plus q, the number of x's that we have on the left hand side, has to be equal to the number of x's on the right hand side. P plus q has to equal b, and the constant p, q, which is just a number, it has no variable in there, would have to be equivalent or equal to c. That's the basic idea of how we come up with the factors of a quadratic expression or a quadratic equation. Let's just take a look at a quick example here. All right, here's a quadratic with 3 terms. We would call this a trinomial. It's already in our kind of standard form with equal to 0 on the right-hand side. So as a bonus, I can also show you the solutions very easily because it's going to be able to use this zero product property to get them. Well, the idea here is trying to figure out what are the p and q of these two factors. We kind of already understand it's going to be x plus something times x plus something. That ensures that the x and x multiply to get an x squared. But we need to find the p and the q that add to b. B in this case, you got to be careful, actually includes that negative sign. So two numbers have to add to -9. And then they also have to multiply together to equal c. And in this case, c is our 14 there. Well, you can kind of start thinking about all the different factors that multiply to 14. 1 and 14 or 2 and 7. There's not really that many different factors. Because they multiply to a positive 14, they're either both positive or they're both negative. Well, in order to add to -9, I guess that kind of forces them both to be negative. And it looks like we would need to have a -7 and a -2. Or -2 and -7. The order doesn't really matter here. But that does check out. -7 and -2 add to -9, and they multiply to 14. So that should complete our two factors here, x minus 7 and x minus 2. Now at this point in time, we go ahead and use the zero product property that allows you to take this first factor and say, well, that could equal 0. It's one of the ways that two things could multiply to 0. Or maybe the other expression, the other factor, x minus 2, could equal 0, because that's the only other way that the whole product could equal 0. And then using the addition property from linear expressions that we just talked about, and then using the addition property for equations, we can add 7 to both sides and get x equals 7. And in this case, we can add 2 to both sides and get x equals 2. So we have two solutions, x equals 7 or x is equal to 2. All right, now it's important to remember that this particular technique of just finding your p and q, very quickly, that is really only in the case of where a equals 1. And that's the coefficient of our x squared, the biggest power in our quadratic. So we actually call that a the leading coefficient. What if the leading coefficient is not 1? That means we got to take a look at a more general case here. For a general quadratic expression, we would have ax squared plus bx plus c. In this case, a doesn't have to equal 1. Well, in order to factor that, we're looking for two linear factors. And a linear factor would be something of the form ax plus b, but I'm already using a's and b's here. So I'm going to kind of go back to using lower down the alphabet. Maybe a px plus q would be a linear factor. And an Rx plus x would be another example of a linear factor. We really want so that this is true for px plus q times rx plus s to then expand out and be equivalent to ax squared plus bx plus c. Well, I'm going to do that. I'm going to expand this out, as terrible as that's going to be. Px times rx. It's important to know that at least that gives us the x squared for our quadratic, but the coefficient in front of that is going to be p and r put together. So pr is our coefficient there, times x squared. Distributing further, we got the outside two terms, px and an s, and I'm going to make sure that we have an x, and the coefficient is going to be p times s there. The inner two terms also have an x. That's going to be a coefficient of qr. And then we have the final two constants multiplied together, qs. With the right-hand side, just copying and pasting down to the next line. Okay, I'm going to start trying to group these middle ones together, form all of our x's, and then I'm just going to quickly equate coefficients so we get a strategy that we can use here. Now the coefficients of x squared on both sides have to be the same. So on the left-hand side, I've got PR, and on the right-hand side, the coefficient of x squared is equal to a. So PR and a have to be the same number. Looking at all of the x's, the coefficient on the left-hand side, when I combine them together, is the sum of PS and QR. And that has to be equal to B on the other side. Okay? Finally, we get to our constants. I'm just going to use C to represent constant here. On the left-hand side, the only constant that we have that has no x's is the value QS. And on the right-hand side, our constant is C. Okay, well, with these three equations, you might even be able to use a little bit of a guess and check kind of method. You're going to be trying to think about, what factors of A are there? The various different factors, well, that's going to be your P and your R. What are the different factors of C? That's going to be your Q and your S. And then hopefully if you've picked those four values correctly, then you can figure out and make sure that PS plus QR does add to B. Just guessing and checking. There probably aren't that many factors depending on what the values are for A and for C. But I'm going to show you the more sort of routine method that you can use to factor. This doesn't always work if things can't factor properly, but it's called the AC method. And it uses these three equations. We're just going to kind of tidy them up a little bit and come up with a routine. What I mean by that is I'm going to combine two of these equations into one. The x squared equation, where PR equals A, and the C constant equation, the QS equals C equation. If I multiply them together, then with P times R and Q times S, well, that should just be the equivalent to A times C. That's actually where we get the name AC method that we're going to see in a moment. And then the other equation that I'm not going to do much with, PS plus QR equals B. Okay, now I can rearrange the order of multiplication by using both our commutative and associative properties and reorganize this first equation. So I have P times S and Q times R. That still equals AC, and PS plus QR equals B. Well, now you can kind of see that there's a little bit of symmetry there. We've got a PS, which is some number, and we've also got a QR, which is some number, and we're kind of back to what we did in the more simplified case. We're looking for two numbers that multiply to AC, and to those same numbers, I'll also have to add to B. This leads us to our AC method, or at least that's the theory behind it. It's a lot quicker in practice. Let's just dive into an example here. I'm going to jump right into a quadratic equation that we're trying to solve. In this case, we have A is equal to 3. Be careful with the negative signs. B is negative 5, and C actually is negative 2. All right, so we look at this AC method. A and C multiplied together. Well, that would be our 3 and our negative 2. And that gets us a negative 6. And we're going to be looking for two values that multiply to AC. Those same two values have to add to B. So there aren't really that many factors of 6. 1 and 6, 2 and 3. They multiply to be a negative, so only one of them can be negative. That's the trick here. 2 and 3 certainly add to 5, so does -2 and -3 add to -5, but two negatives can't multiply to -6, so those aren't the factors we're looking for. In fact, it's actually that we need a -6 and a +1 because those add to -5. You gotta be a little careful here. Okay, so we've figured out the AC part of it, but there's actually quite a lot of steps to this method. First of all, I kind of want to work backwards and take what was only 3 terms, a trinomial, and actually kind of break that down into 4 terms, because usually when we FOIL out 2 binomials, we get 4 terms. So I'm going to kind of reverse the whole process. We're going to do something called decomposition here. Decomposition is where we keep our 3x squared, we keep our -2, but the middle term we split up. Another way to write -5x is actually to have -6x plus 1x. That -6 and 1 were the 2 coefficients that we basically just found using our AC method. We know that those add to -5, so we know that -6x and 1x add to -5x. All right, we've got that decomposition step done. Now it's time to kind of reverse the expansion of FOILing out our px into rx and so forth here. And we reverse that by factoring. We do that in groups, and so we actually would typically call this factoring by grouping. I'm going to be looking at the first 2 terms here and seeing what they have in common at the most. The biggest common factor. The biggest common factor of 3 and 6 would be just 3. I could just as easily have factored out a -3, but I like the positive in this case because, well, if I factor out the x as well, that leaves me with x minus 2, which is quite nice. Out of these last 2 terms here, there's not really a lot to factor. There's nothing in common with a 1x and a 2, really. However, you can always factor out a 1. That's not a problem. I can factor out either a +1 or a -1. Factoring out a +1, however, leaves me with an x minus 2. And that's great because you'll see that in both of these 2 different groups, I have a common factor. So I can factor one more time by pulling out that common factor. Our common factor in this case is our x minus 2. And pulling that from our first grouping, we're left with a 3x. Pulling it from our second grouping, we have a +1. Putting the brackets in there, we can see that we factored right down so that we have 2 binomial or just linear factors. Great. All right, we've finished the factoring by AC method strategy. We have the AC part first. That allows us to decompose the middle term there. And then we can go ahead and group into separate little factors, and we should hopefully find a common factor of each of those groups. Now we can use the zero product property. Because the right-hand side equals 0, one of these factors would need to be 0 in order to form that product. Either 3x plus 1 equals 0, or x minus 2 equals 0. We use the properties of addition and multiplication for equations. I'll start with the easy one by adding 2 to both sides of the second equation. We get x equals 2. And for the other equation, we need to subtract 1 from both sides, adding a -1 to both sides. And then I need to divide by 3, which is equivalent to multiplying by 1/3. And there's my 2 solutions. Either x is equal to -1/3 or x is equal to 2. You might have been able to get that a little bit quicker by using the guess and check method because there weren't that many different factors of 3. There weren't that many different factors of -2. So if I just maybe guessed a few times, I would have come up with a 3 and a 1 probably, and I would have come up with a 1 and a 2, and then it's a matter of sorting out which one has a plus sign and which one has a minus sign, and you check your answer by expanding. Now, of course, you might be watching this and thinking, why should I bother factoring this when there's a perfectly good formula for solving a quadratic? Well, okay, sure. We're going to get to that in just a moment, but keep in mind that factoring is a useful skill in so many more applications than just quadratics. It's about maybe the first time you ever really see the factoring idea. But it comes up all the time in all kinds of equations. And no matter how complicated it is, if one side equals 0, we probably could just factor a whole bunch as much as possible and break it down into smaller pieces. Those smaller pieces might be linear, like in these examples, but those smaller pieces could have trig functions, exponential functions, and logarithms, and all kinds of things. Factoring is just a useful skill, no matter whether or not you have a formula for solving it conveniently or not. So let's get to that quadratic formula finally. Okay, the beautiful gift of the quadratic formula. That's where we have a quadratic equation in the form of ax squared plus bx plus c equals 0. And a formula to solve for x should be something that allows you to just plug in only the coefficients and use some basic algebra to get x. In this case, it works. X is equal to always just negative b plus or minus the square root of b squared minus 4ac, and all of that divided by 2 times a. It's important to note that this worked with quadratic equations, but once you start getting up into higher degrees, the formulas get more complicated, or maybe once you get to at least an x to the 5 in there, you're going to find that formulas don't even exist anymore. So really want to appreciate this one. The thing with this formula is that it actually may give you 2 solutions, may only give you 1 solution, or maybe no real solutions. We'll see an example of each one. Let me give you an example where we could get 2 solutions. X squared minus 3x minus 5 equals 0. All right, we're not going to use the AC method on this one, although maybe we could. Let's just try the quadratic formula. We're going to have negative b, be careful because that's negative 3. We have a plus or minus, and that's typically how you find out that you get 2 different solutions. Inside the square root, again, be careful with the negative. We have a negative number squared, negative 3 squared minus 4 times 2 times negative 5. Okay, it's a pretty big square root, so sometimes you want to put a little tail on your root symbol or your radical symbol so you know what's in the root and what's not. And then all of that divided by a big old 2 times a, 2 times 2. Simplifying things down a little bit, we have negative 3. That's going to be positive 3, plus or minus, and inside the square root, a negative number squared is positive. So that's just going to be negative 3 times negative 3 is 9. And then we have negative 4 times 2, negative 8, times negative 5, which is 40. Perfect. And then all that divided by 2 times 2, which gives us 4. Simplifying that down a little bit, 3 plus or minus the square root of 49. That's nice. All divided by 4. Now in this case, that root 49 worked out nicely. That just gives us 7. But you don't always get a perfect square inside there, of course. So it's important to know how to simplify radicals. 3 plus or minus 7 divided by 4. And we get 2 different solutions out of this. We can either get x is 3 plus 7 over 4. That works as 10 over 4, or 5 over 2. And our other solution would be x equals 3 minus 7 over 4. That gives us negative 4 over 4, and that equals negative 1. Now, of course, it's kind of important to know that you've done the work correctly. So if you want to check your answers, you can take these 2 values, these 2 roots, and put them back into the original equation. Kind of an easy one might be putting that negative 1 in. 2 times negative 1 squared is 2. Minus 3 times negative 1 is 3. All right, that makes 5. Subtract 5. Perfect. That equals 0. And I'll let you check the other solution as well. Okay, well, how about I just switch a little sign here so we don't have to do all of that math all over again from scratch. Okay, in this example, I've just changed that final coefficient from a negative 5 to a positive 5. And see how that affects our answer here. Well, most things are going to be exactly the same. That is, at least until we get to our part inside the square root. Now I have negative 3 squared minus 4 times 2 times positive 5. And that's going to change the sign of that term. Now, when I expand things out, I have 3 plus or minus the square root of 9. And this looks like it's going to be negative now. That's going to be minus 40. That causes a bit of a problem because now we have 3 plus or minus the square root of negative 31 all over 4. Now, the square root of a negative value isn't a real number, so in this case we get no real solutions. Okay, and as a little bonus, maybe I'll just give you a very quick example of where we might only get one solution. Here's a very nice quadratic that you could also just as easily factor. But instead of factoring this time, I'm going to use the quadratic formula and show you why you can sometimes only get one value from it. In this case, I have x equals to negative 2 plus or minus the square root of 2 squared minus 4 times a, which is 1, and c, which is also 1. And as I'm writing down this whole formula, you might see what's going to happen here. Inside that square root, I have 0. 2 squared minus 4. Square root of 0 is just fine. That just leaves us with 0. So I end up with negative 2 over 2, which just leaves me with x equal to negative 1. You could have just as easily factored that as x plus 1 times x plus 1. And we see there's actually a repeated factor there. We could just as easily also write that as x plus 1 squared. So sometimes instead of saying there's only one solution, we may also say that it's a repeated root. Negative 1 is actually repeated because it's in both of the factors. Now, the key here to figuring out if you get two solutions, one solution, or no solutions at all, that's all dependent on that b squared minus 4ac, the stuff inside of the radical. Now, there's a name for that. It's called the radicand. That's the stuff inside of any radical. But because this is so important to quadratics, we call it the discriminant. The discriminant will tell you the nature of the solutions that you get. So b squared minus 4ac, that's called our discriminant. We have three cases. If b squared minus 4ac is positive, well, then we should be able to take the square root of it. And then we're going to add and subtract to get two different roots. If b squared minus 4ac is equal to 0, we can still square root it, but then you get a square root of 0 equal to 0, and adding or subtracting leaves you a repeated root, or just one root. Now, if that discriminant ends up being negative, then we cannot square root it to get a real number. So we say no real roots. All right, well, now you probably already have a scientific calculator or maybe a graphing calculator, and a lot of those more modern, more powerful calculators just have a built-in function somewhere, maybe in a menu, where you can solve a quadratic equation and it just spits it out for you, where you have to just put in your a, b, and c. So it's pretty handy. But it's important to know where it comes from. And even then, I've just kind of given you a formula. Where does that formula come from? If you want to know more, that comes from a long process that is called completing the square. And that's where you take a general quadratic equation, ax squared plus bx plus c equals 0. And by adding some things to both sides and factoring in a specific way, you can actually get that equation so it only involves a single x inside some brackets squared. And then using some properties of equations, you can solve for x. To get rid of that bracket square, that's where you get the square root. But the completing the square process is maybe not the most efficient way of solving an equation. It's still very useful later on, we'll see, when we maybe want to graph quadratic equations. And it's useful to rewrite an equation in a more useful way, but I'll save that for a different video. Finally, I'll just recap one other major factoring technique that we use with specifically quadratics in a particular form. A very quick factoring formula is applied whenever we have something where we have a difference of squares, a squared minus b squared. So that would be when we have an a plus b and its conjugate a minus b put together. We can use that in a little bit more powerful form, where instead of a and b just being numbers, I'll just replace those with some capital letters to represent full expressions. That can be very useful for solving some quadratic equations like x squared minus 16 equals 0. So seeing that this is in fact a difference of squares, we can go ahead and factor it right away into an x plus a 4 and an x minus a 4. And if that equals 0, we can use the zero product property to say that either x plus 4 equals 0, that gives us x equal to minus 4, or the other factor, x minus 4 equals 0, which would end up giving us a plus 4. So we can write that as x is equal to either plus or minus 4. And this is so useful, it's not even only used for quadratic equations. We can even go as far as maybe something like 4x to the 4 minus 25 equal to 0. If this happens to be something squared, and it is, it's 2x squared minus 5 squared, then we can use our difference of squares formula and factor it right away into 2x squared minus 5 or plus 5 and 2x squared minus 5 or plus 5 as long as we have those two conjugates. And that simply just made things a little bit easier. We took a quartic equation and factored it into two quadratic equations. And one of those factors had better be equal to 0. Cool, so the difference of squares formula comes in handy for factoring polynomials. And as a further bonus, you may have guessed since I numbered that number 1 that there's some other quick little factoring formulas coming along. There is a factoring formula for a sum of cubes as well as a difference of cubes. To factor a sum of cubes, we factor that into a binomial, a plus b, and a trinomial with 3 terms, a squared minus ab plus b squared. And it's fairly similar for the difference of cubes with a couple sign changes. That allows you to factor things that are even beyond a quadratic pretty quickly, like x cubed plus 8 or x cubed minus 8. Since 8 is a perfect cube and so is x cubed, it looks like we have a sum and difference of cubes, where our capital A is just our x, and our capital B is 2 because 2 cubed is 8. Filling out the rest of the formula, that leaves us with these nice factors where we have a linear and a quadratic. And at this point in time, maybe you can try factoring those quadratics further. Depends on how nicely things turn out. So I'll leave it there. That gives you a lot of tools and techniques for figuring out how to factor various different linear and quadratics. And while the ideas are still mainly based upon the fact that you can take a linear equation or a quadratic equation or any equation and add something to both sides. And you can also multiply both sides by a non-zero value. Those fundamental properties there are used everywhere. And factoring is mostly based around the fact that you can use the zero factor property. So that is going to be mostly used all over the place, not just in quadratics. Keep those things in mind. Thank you for watching, and I'll see you in the next video.